All right. So the last time we met, we introduced a couple of the laws of chemistry. One is the conservation of mass, right? Conservation of mass. Mass is not created or destroyed. Therefore, if I have, for example, a chemical equation where A and B come together to form C and D, and I say all the material that I have here is going to be converted to C and D, and I say 1 gram of A reacts with 6 grams of B, and I get 2 grams of D. From that, we should be able to know how many grams of C I'm going to be able to get, right? How many should I get there? 5. That's right. The mass of our reactants has to be the same as the mass of the products in chemistry. Okay? The other law that we looked at was a law of definite proportions. Definite proportions, which essentially is saying that if I have a sample of a chemical over here, A2B, right? The amount of A relative to the amount of B in this pile of this material, right, is the same as the amount of A to B in this pile of the material, because it's the same type of material, right? So the number of molecules of, atoms of A per atom of B is the same ratio here. The mass of A is the same ratio because it's the same material, right? So the law of definite proportions. Another law that we're going to introduce here is what's called the law of multiple proportions. And, you know, it's kind of a shame that they have a law called the law of definite proportions and a law of multiple proportions, but it's not terribly, neither of these laws are very restrictive or that important. But the thing that this shows us is that if you do take two chemicals, in this case we're taking sulfur, which is yellow, and oxygen, which is red. If you do take sulfur and oxygen and react them, you'll get a product. This is sulfur dioxide. But it's possible to change the conditions and different temperatures, right, different pressures, and change how the sulfur and the oxygen will come together. You could actually get a different substance. All right, so there is, and it's, you know, you kind of already realized this with our examples of O2 and O3, right? Oxygen exists, but also ozone exists. So somehow we have 2 oxygen atoms that like to pair up, and scenarios also where we have 3 oxygen atoms that like to pair up. So it's possible to get other types of combinations, and I don't know if you've caught on to this one yet, but there's water, H2O, but there's also H2O2. H2O2 is hydrogen peroxide, right? So both of these are combinations of hydrogen and oxygen, but there can be multiple ways in which they come together. All right. So, we're going to talk a little bit more about chemical equations, and then we're going to finish up this chapter, and we'll be on to the next. We've already mentioned a handful of these things in chemical equations. First of all, we have our reactants, the things that are reacting together to the left of the equation. An arrow, which means yields or produces. So the way that we talk when we're trying to translate this chemistry is 2 HCl's plus 1. Now remember, if there's no number there, it's a 1, right? So 1 calcium carbonate reacts to yield, that's what our arrow means, 1 calcium, 1 calcium chloride, 1 water, and 1 carbon dioxide. And then our little S down here, do you know what that S refers to?
Solid.
Solid, that's right. So we have solid, liquid, and gas, okay? And we're going to make sure that we're aware of what AQ means. This is, you know, solid, liquid, and gas we kind of grow up understanding and talking about, but you don't talk about AQ, which means aqueous, much outside the chemistry class. So aqueous means that it's dissolved in water. So if you put a solid into water and the solid dissolves, then you'll say your solution or your material is aqueous. So in that way, remember the other day you were saying or asking about, well, how do you describe a solid that's mixed with another compound? And I said we don't really have a way to do mixing two things together. We don't have a good chemical formula to write other than in water, because a lot of chemistry occurs in water. So if we write something like this, NaCl aqueous, that aqueous means it's dissolved in water. So in a way, this is a compound in water. So it is kind of like a mixture right there. Okay?
Oh, okay.
Okay, so these equations, because the number of grams of material and the number of atoms of reactants and products have to be the same, right? We have to make sure our equations are balanced. Now, there's plenty you can learn without balancing every equation. So sometimes I might write an equation and talk about something else other than taking the time to balance it. But ultimately, if we want to know the ratio of the different compounds that are reacting or that are being produced, we need to have a balanced equation. Now, to balance this equation, you can't change the coefficients. You can't change the subscripts. So let me show you an example of what I mean. If I want to show an equation of hydrogen gas coming together with oxygen gas to form water, and I want to balance this equation, I can't look here and say, all right, on the left side of the equation, I have how many hydrogens? Two. So I have 2 hydrogens. And how many oxygens? 2. And on the right side of the equation, how many hydrogens? 2. Whoops. Equals 2. How many oxygens? 1. I can't just say, okay, well, hydrogen coming together with oxygen to form water. I'll just change that to a 2 to balance it. Because now this isn't water, right? This is hydrogen peroxide, like we mentioned. So I can't change the 2 there. I have to only change the coefficients if I want to balance it. All right? Okay. So in this case, I see I need more oxygen to balance it. So I'm going to start by putting a 2 there. After I put the 2 there, then I have to kind of recount. And I see I have 4 hydrogens this now and 2 oxygens. And then I can come back over here and see what I can do to increase my number of hydrogens. And what do I have to do to get the appropriate number of hydrogens on the left?
2.
Yeah.
Coefficient.
That's right. 2. So when we do balancing, we only change the coefficients. All right. And if I did the counting again, I'd see that I got 4 there and I still have 2 oxygens. So I'm balanced. Right? Okay. Very good. So now we're going to take some time and make sure we know how to balance equations. Here's our first example that we're going to work with here. This is C8H18. C8H18 is the main component in gasoline, automotive gasoline, octane. Combining it with oxygen gas to form, and this is what happens when you burn octane in your car or on the campfire or wherever. You get carbon dioxide and water as our products. Okay, so talk me through this. How is it that I'm going to balance this equation? What am I going to do? First, I need to make a list, right?
Yeah, right.
So what elements do I have on the left?
So we have C is what?
Carbon.
Oh, I'm sorry, carbon.
Yep.
So we have 8 carbon.
8 carbon, okay.
and then 18 hydrogen,
All right, 18 hydrogen,
and then two oxygen.
2 oxygen. Very good. And on the other side?
We have 1 carbon,
All right,
3 oxygen,
3 oxygen. Whoops.
and I guess I should go with hydrogen.
No, that's okay.
Well, 3 oxygen, okay, and 2 hydrogen.
2 hydrogen. I had these oxygen in the 2 mixed up. Okay, so we got 8, 18, 2, 1, 2, and 3. All right, so how are we going to fix things?
So we need to use the coefficient in front of now the one on the left. Tell me what that is. Yeah,
C8H18. Yeah, you can just call it. You can call it C8H18 if you don't know, but that's octane.
Okay, octane. So if we write a coefficient in front of the C, it's because that's already combined. It covers everything, right? It would be.
Yeah.
It would make that C into a 16 and make the hydrogen to 36, right?
Yeah, that's
this
right.
Is just for clarification, right?
That's right.
Okay. Okay, I just want to make sure I understand this. Yeah, thanks.
Yeah, those are the locations that we have to manipulate when we want to balance an equation. Yeah. So we need more carbons on the right. Is that right?
We do, yeah.
So how can we get?
So if we put a 4 as a coefficient there, we would match it, right?
A 4?
Yeah.
Well, that would only give us how many carbons?
Oh, I'm sorry. I'm looking at, yeah, it would have to be an 8, right?
Okay, yeah, 8. 8. So then that gives us 8 carbons. How does that affect our oxygens?
Okay, so it would be 16 there on the right.
16 here, but you have to include that one for now, right?
Oh, that's right. Oh,
So,
we do?
Yeah, well, I mean, it's
Oh,
one.
yeah, that's right. That's right. It's still okay. Right.
All right. Good.
Okay.
So how about hydrogens? Did we change hydrogens?
We haven't changed it yet.
Okay, so it's still 2. So by putting the 8 there, and every time you put a coefficient, it's good to recalculate everything. We have the same number of carbons now. Hydrogens are still different, and oxygens are still different.
Okay, so if we did 9
waters,
hydrogens, that would
9 waters there.
Right.
Okay, good.
That's right. I'm forgetting it's okay. And that would change. And that will also affect the oxygen, right?
Yep. So we'll have to recalculate everything, which is what we expect.
Okay. So it would make it 18 hydrogen there, right?
18 hydrogens. Good.
But it's going to up the oxygen, right?
Yeah. What is it going to do to it?
So we're going to have 16 plus 9, right?
Yeah.
So
25. 25 oxygen. All right, great. And we still have 8 carbons, so I'll just write that down. This is our new calculation there.
Okay.
Oh, look, we got 8, 18, 2, 8, 18, 25. So we're getting close, right?
Getting close. Oh, yeah.
So what do we have to do now? We need.
I wish that was 26 there.
That's right. So it's kind of.
So it's going to be a fraction, right?
Yeah.
It can't be a fraction?
Well, it can temporarily. We can put in there 12.5, and then that gives us 25, right?
Right.
But you're right. We can't leave it as a fraction. But when we have a fraction.
Okay, so we have to, go ahead.
Yeah, what are you going to thinking? What are you thinking?
Well, so we have to find the common.
Yeah.
I forgot what's called.
Common denominator, yeah. We just have to actually multiply this by 2, right?
Okay.
If we multiply that by 2 and multiply everything else by 2, we'll have it, right?
Oh, okay. Okay.
So we'll make this 2. This will be our 25. This will be 16 now, and that will be 18.
I see.
Now, all of these numbers double, right? 16, 36,
Okay.
and 50. Whoops, 16. Right?
Right. Gotcha.
Okay, good. So we did it. 2, 25, 16, 18. Excellent. So, recap. Essentially, we went back and forth. We made ourselves a list so that we could follow along well. Carbon, hydrogen, oxygen. We counted them up, which is critical. You need to know how to count up elements in compounds at this point. And then we made adjustments to the coefficients. We didn't change any of the subscript numbers, right? The numbers down here, because that changes the compound. But we changed the values of the coefficients, going back and forth. When we were almost there, we had a fraction in here, and we kind of used that as a temporary station, and then recognized that we had to multiply everything by 2 to get to where we wanted to be. Okay? Excellent. Good job. Okay, let's look at the next one here. We want to make sure that we can always balance the equations when necessary. Okay, here's a crazy one. You see this crazy one?
Yeah. I do.
Okay, so I'm going to teach you now kind of a way to make crazy ones a little more manageable. Okay, actually, let me write this one down on the paper for us so we can work off of our paper. This is NH4 ammonium, PO4 phosphate, plus barium acetate, and the products are barium phosphate and ammonium NH4 acetate, C2H3O2. Okay. Now, looks super scary, right? How in the world are we going to be able to keep track of everything? And, you know, without the little tip that I'm going to give you here, we would essentially look at this and we would say, all right, let's get to it. Let's count up the nitrogens. We got hydrogens, phosphorus, oxygens, barium, carbon, and then more hydrogens and oxygens, right? We would just make a list, count them all up, and there's nothing wrong with that. Nitrogens, hydrogens, phosphorus, oxygens, barium, calcium. That's what you got to do. Where?
Are you missing the over at NA4?
NH, nitrogen, hydrogen.
Oh, that's H.
Yeah,
oh,
hydrogen.
Okay. That wasn't H, sorry.
Oh, sorry. Anyways, that's what you would do.
Gotcha.
That's what you would do. But I'm gonna show you. Hopefully, you can read my writing, okay? But I'm gonna show you a little trick here that we can do. And what the trick is to look at clusters to find groups amongst this equation.
Okay.
Can you see any clusters in there that seem to be the same on the left and the right? See this NH4 group here?
Oh, okay.
And you see the NH4 over
yeah,
here?
That's an H word, yeah.
All right, so instead of writing down nitrogen and hydrogen like that, I'm just going to write down NH4. And we're going to count that as a cluster. Any others that you see?
The barium?
All right, barium.
And then the parentheses are kind of throwing me off, but I guess you just ignore them, right?
Well, actually, the parentheses kind of help us find those clusters. See that? There's a C2H3O2 there, and a C2H3O2 over here. Can you see that?
Right.
So that's another one. C2H3O2, which is called acetate. Okay, C2H3O2, that's another cluster. And I think we just have one more. What's the last one?
The P, what is that?
PO4.
PO4, yeah.
Okay?
And what is that?
That's phosphate. That's the phosphate ion.
Phosphate, okay.
And we'll talk more about that later on. Okay, so how many of these NH4 groups do I have on the left?
Well, so times 3.
That's right, I have 3. I have this 3 times. How about on the right side?
Just 1.
Yeah, just 1. How about the barium? On the left and then on the right.
Okay. On the left, is it 2 or is that 2 just for the cluster?
That 2 is just for the cluster, and that's what that parenthesis is helping us see.
Gotcha. So then just 1.
1.
And 1 on the, oh wait, is that 3 down there?
Yeah. Yeah.
Okay,
3.
Okay.
Now for this acetate.
Okay, so now we're times 2.
Yep.
I mean 2.
2.
And then 1 on the right side.
That's right. Very good.
Okay. And then the PO4 is just 1. And then we have 2 on the right side.
Excellent. Very good. So, what should we do first to try to start to balance this stuff?
Okay, so we could I'm thinking put our little space in front of for the coefficients.
Yeah. Yeah. What are we going to put in there?
Okay, so we're going to, just like that, right? Okay. So then on the right, well, let's see. So on the right side, we would need, I'm sure this is going to have to be refined as.
That's fine. That's fine, yeah.
I would say if we start on the left, that first one we would keep it blank. So we have 3 of those, and then we need to even it out on the right side. So we would put 3 in front of the NA.
All right, NH4. So how many NH4s is that going to give us then?
Well, then that'll give us
3. 3. What else will that change?
Okay. Oh, that's right, because they all go together, don't they?
Uh-huh. So it's going to make 3 here?
Do they?
Yeah.
Is that, okay.
These are together, that's right.
They're together? Okay, so that's going to change the... Okay, so that'll make that cluster down there is
3. Very good.
Okay.
All right, so that got these 2 the same. Very good. What's next?
So I guess we would do the same thing with the barium.
Okay, put a 3 here.
Yeah, 3 there.
All right, so that gives us 3 bariums on the right. And how does that change this over here?
Well, yeah, how does that change? That's going to make it 6, I guess, right?
Yeah, 6. Okay, excellent.
Okay, so we're almost there, right?
Yeah, we got these 2 are the same now. Very good.
Okay, so we need to, now can we just cross multiply on that or well, I guess we just,
Just got to keep working until we get these the same. So we got some phosphate issues here. How are we going to adjust that?
Well, if we
Here's the phosphate up here, right?
yeah, I see it.
Looks like we're going to have to put a 2 here, right?
Okay.
True, because if we put a 2 there, then that's going to give us
put 2 there.
2 phosphates, right?
Right.
But it's also going to change this up here, right?
Yeah.
It's going to make
so
what?
It's going to make that 6.
6.
On the,
Okay.
okay. And, wow.
Now it looks like we need more ammonium, right?
Yes, it does.
So where are we going to, instead of 3 here, what do we got to put?
6.
6. Yeah, we're going to have to change that to 6.
Oh, I see. Okay.
So that gives us 6 ammonium, and then how many of these C2H3O2s does it give us?
It's going to give us 6.
6. All right, so we're at 6, 3, 6, 2 here, and 6, 3, 6, 2 there, right?
Oh, okay.
So that was 2, 3, 1, and then 6. You see that?
Yeah.
Okay. Good job. So essentially, what we learned from that is a couple things. One, we work in clusters, and when you work in those clusters, my writing's not very good. It's easier to see when it's typed like this. Working in those clusters allows you to balance those equations a little easier. And 2, the other thing we learned is you just got to keep at it. Just keep going, keep trying things, going back and forth. If it doesn't work, you just throw the piece of paper away, start over, and take a deep breath, right? So, good job. All right, so that ends our first chapter. And now we'll get into